This experiment is on mechanics of plate fixation. We're going to look at the loading of the plate screws. We have three configurations of plates. We have long plates. They're all the same size, but they have a different configuration. Here we have a long lever and a short lever. Here the levers are the same. Here we have a short lever and a long lever. Now these weights, they represent the pull-out strength of the screw. The pull-out strength of these screws in each configuration is the same. What we want to know is how much pull-out force do we have to have on the other side in order to have the screws come out of the bone. Now, I would like for you to take one weight and put one weight on each of these bones. You see, the pull-out strength of this screw is fairly low. Why? Because the force that you put here on the longer lever arm pulls the screw out of the bone. Now, place more weights on these two bones. The pull-out force here is double the pull-out force here. Why? Because the lever arm is different. On this model, you have a lever arm which is equal on both sides. The pull-out force is almost equal to the screw pull-out strength. Put more weight on this one. Here you see we need 4 times the pull-out force in order to pull this screw out of the bone, meaning that we have a long lever arm here with the short lever arm here. This demonstrates the holding power of this screw. In this experiment, we're looking at the working length of the screw. The working length of the screw is represented by the amount of threads that are in the cortex in these different sizes of cortex. The configuration is the same. I would like for you to put on a torque force on each of these to see where the working length of the screw is highest. We have a monocortical screw here, a monocortical screw here, and a bicortical screw here. Where is the working length the highest? So you have seen that the working length is the best if you have a bicortical screw. It is very good if you have a thick cortex, even if it's monocortical, but the monocortical screw in a thin cortex has the shortest working length. In this experiment, we want to test loading of the plate. We have 5 different configurations, and we would like to test the bending stiffness of the plated bone models by taking them in our hands and putting a bending load on each model. The plates have been placed on the tension side of the bone. When we put a bending load on this construct, I am actually closing the small gap, so there's a lot of contact. Not only the plate is contributing to the stiffness, but also the bone. We call this load sharing. As I put a bending load on the compression side, I am opening the gap, and no load sharing can take place. These models have the same screw configuration in the plate, but this one has a large gap. If I put a bending load on a bone with a large gap, the gap does not close, and no load sharing can happen, no matter in what direction I apply the load. Here, I have the same gap, but I have 2 screws which are very close to the gap and 2 screws which are further away from the gap. Now we want to put a bending load on the tension side of this bone. I'm putting a bending load here, The stiffness is not very high, but I have an elastic plate which will withstand bending loads for a much longer time than if I had two screws which make this much stiffer. If this bending load continues, at some point the plate will break. The fifth bone that I have here represents a fracture which is multi-fragmented in the middle. I'm putting a bending load on this, and you see this is very stable. Why is it stable? Because the secondary fragments are also carrying part of the load. So the plate and the bone are both carrying the bending load that I'm putting on this. However, as soon as I reverse the load, the fragments cannot interdigitate, and thus no load sharing is possible anymore. Now, please try the models yourself. So now let us discuss the results of this exercise and what you can learn.
In the online faculty support packages, you can find faculty guides for each station and, where appropriate, topics for discussion and frequently asked questions. In case of questions, please send an email to templates@aotrauma.org.